Exponential and logarithmic models. Exponential functions can be used to model real data if the data exhibits rapid growth or decay. When the scatter plot of the data shows a very rapid increase or decrease, it's possible that an exponential function can be used to model the data. In exponential regression, most utilities give the best fitting exponential model in the form of y equals a times b to the x. Example 1, insurance premiums. The monthly premiums for $250,000 in term life insurance over a 10-year term period increase with the age of the men purchasing the insurance. The monthly premiums for non-smoking males are shown in the table. An male age 35 would pay $123 monthly premium for 10 years in a 10-year term insurance policy. Age 40 years would be $148 a month, and so on. So let's graph the data in the table with X as the age and Y in dollars. So go to your graphing utility, to Stat, and we'll edit. Enter your X's into list 1. And your Y's, your age, the monthly premium in for the list 2, for the Y's in your table. All right, double check and make sure that you haven't made any entry errors. Make sure all of your entries are correct. And we can go to y equals and turn the plot on this way, or you can go second y equals and turn the plot on or off in that menu. Now that the plot is on, we can do a zoom stat, and you see the data points graphed for you. Now we want to create an exponential function that models the premiums as a function of age. So let's go to Stat, and we will calculate an exponential regression. Just keep going down to option 0. And remember, do not get exponential regression and power regression mixed up. They are different things. Default is list 1 and list 2, where we already have the data. And we can go ahead and store this so that it will put it into the equation editor for us. So this is y equals 4.04 times 1.09 to the x. Let's graph the data and that exponential function that models the data on the same axes. There we see. And you can see that it is not an exact fit, but it is a fairly good fit for the data in the table. Example 2 is e-commerce sales. E-commerce is taking a bigger slice of the overall retail sales pie and is growing far faster than retail sales. E-commerce sales in the U.S. are projected to be $434 billion in 2017. You can see that on the table, which is more than double the 2010 sales, which were $171 billion. The table gives retail trade sales by e-commerce in billions of dollars for the years 2000 to 2017. Let's graph the data with X as the number of years after 2000. So let's Stat, Edit, and remember we are aligning our inputs to the year 2000. And let's go to list 2 and put our sales in billions of dollars there. And double check to make sure that we've not entered anything incorrectly. And go to y equals, let's erase the function that we had before. Our plot is already on, so let's do another zoom stat so we are getting a window around those new data points. Now let's find an exponential function that models this data, and x representing the years, the number of years after 2000. So we'll go to stat and calculate, go down to exponential regression. We're automatically taking from list 1 and list 2, and let's store the regression equation so that we can see the graph later for part C. Calculate, and notice where they've put A and B. So y equals 35.6 times 1.17 to the x. Let's graph the data and the function on the same axes. Since I've saved that equation in there already, and we've already done a zoom stat, that's all going to fit nicely in that window. And what does the model predict the online sales revenue to be in 2025? Let's talk about what 2025 is. 2025 signals 25 years after the year 2000, so that's an x value. Let's go ahead and trace then, is one way to find it. Now when you trace, it's on the plots. We don't want to trace the plots, we want to trace the function that's in y1, and enter 25 because that's 25 years after the year 2025. When you do that, you're going to get an error, and the reason is we only have our window including this data. We're going outside of that data. So let's change our window. Change our window to go to an x value of 26, and let's do a zoom fit then, and then we can trace. Make sure that you get onto the function, not the plots, and put 25, enter, and we see in the year 2025 that the sales in billions is 1652.9. So we'll write that and put billion after it and label it with the $sign. Constant percent changes. If the percent change of the outputs of a set of data is constant for equally spaced inputs, an exponential function will be a perfect fit for the data. If the percent change of the outputs is approximately constant for equally spaced inputs, an exponential function will be an approximate fit for the data. For example, if I had a set of data with these x values, and I have the set of y's for the data, then you can find the percent increase. So percent change here, this would be times 200%, and going here to here is times 200%. This is times 200%, and from here to here is times 200%. So this would be an exact fit for the data. You could even see with putting this into our set of data in the stat editor, and let's go and make sure that in the mode we have our stat diagnostics on. There we go, and then we can take the stat and calculate an exponential regression, and you'll see we can go ahead and store that equation, but the correlation coefficient and the coefficient of determination are both 1. This is perfect. It's a perfect exponential fit. So if I do a zoom stat, you can see those are going right through the data points. Now let's say that we had something very close, the same inputs, and they're equally spaced, but the outputs are maybe just a little bit off. Okay, so the percent change is not going to be the same from one to the next. We can put our new y's in here. And let's calculate a exponential regression, and let's store that regression in y1 and calculate. Again, the correlation coefficient and the coefficient of determination is very, very close to 1, so it is a very close fit, but it's still approximate. If it's anything other than 1, it's an approximate fit. And we can see the graph on that. It just kind of misses a couple of the points here and there, just kind of skims those points. So that's the difference between an exact fit and an approximate fit for data. An exponential model. If a set of data has initial value a when x equals 0 and has a constant percent change r, written as a decimal, for equally spaced inputs x, the data can be modeled by this exponential function, y equals a times 1 plus r to the x for exponential growth. If it was exponential decay, it would be y equals a times 1 minus r to the x. All that does is that it makes this a number bigger than 1, and then with that exponent that is positive or 0, then your graph is going to increase exponentially. And with the decay model, 1 minus r is going to end up being a number between 0 and 1, and with the positive exponent, or x equals 0, you'll have a exponentially falling, a decay model such as that. So your initial value is a, and that makes sense because if x were 0, then all of this to the 0 is 1. 1 times a is a, and that's how you're getting that initial value. Example 3, inflation. Suppose inflation averages 4% per year for each year from 2000 to 2010. This means that an item that cost $1 one year will cost $1.04 1 year later. In the second year, the $1.04 cost will increase by another factor of 1.04. So multiplying it again by 1.04. This gives us 1.04 times 1.04, which is 1.04 squared. And you can imagine if it was to be the third year, it'd be multiplied by another 1.04. So it'd be 1.04 to the third. Fourth year, it'd be 1.04 to the fourth, and so on. So let's write an expression that gives the cost t years after 2000 of an item costing $1 in 2000. It's going to be 1.04 to the t. The initial item costs $1. Now let's write an exponential function that models the cost of an item t years from 2000 if its cost was $100 in the year 2000. For our initial cost was $100, and every year we're going to pay 100% plus 4% of what we paid the year before. That happens every year. So there we have it. Y equals 100 times 1.04 to the t. That way, in the year 2000, t would be 0. 1.04 to the 0 is 1 times 100. We get that $100 cost in the year 2000. So let's use this model now to find the cost of the item from part B, that $100 item, but see how much it costs in the year 2010. In the year 2010, t will be 10. So there's no need for us to graph this. We can simply put this into our calculator from the home screen with an exponent of 10. So that $100 item in the year 2000 is going to cost $148.02 in the year 2010. Logarithmic models. Data that exhibit an initial rapid increase and then have a slow rate of growth can often be described by the function f of x equals a plus b times the natural log of x for b greater than 0. So that is that type of function that increases really quickly and then the growth slows. When using technology to fit a logarithmic model to data, you must align the data so that all your inputs are positive. In other words, I cannot take the log of -2. I cannot take the log of 0. So whatever your year is in this, you're going to have to make sure that you align it in a way that the inputs, all of your x's, are positive numbers. In example 4 on diabetes, the table shows that projections indicate the percent of U.S. adults with diabetes could dramatically increase. Find a logarithmic model for this data with x equal to 0 in the year 2000. So certainly in the year 2000, x would be 0. This 2010 would be 10. So they already have it set up for us and aligned in a way to the year 2000 that all of our inputs are going to be positive. So nothing to worry about there. Let's go ahead and go to our stat editor and enter our data. X's first. There you go. And there we go. And we have a 15.7, just making sure that we have entered all of our data correctly, no typos. Remember, the calculator is going to do something with the data that you feed it. You need to make sure that you have fed it the correct information. So let's find a logarithmic model. We go Stat, Calculate, and we're doing a natural log regression. So there we go, list 1, list 2. Let's go ahead and store the regression equation in y1. So I get this model of y equals negative 12.97 plus 11.85 natural log of x. Use the reported model to predict the percent of U.S. adults with diabetes in 2027. So we could do this in several ways. We could go ahead and type this into our calculator and put natural log of 27 in it. Since I stored it in our graph, I could go ahead and do a zoom stat. And 27 is within the data that is already graphed. So we could say trace and make sure that you arrow up or down so that you are on the y equals, not on the plots, and put 27 in there. You get this 26.09, and that's the percent. You could also go to the table and read off the table when your x equals 27. Get the same thing there. So lots of ways to get that. Now we've rounded quite a bit on the model. My advice would be to use the graphing or use the table here because that has the complete model, not a rounded off approximated model. In what year does the model predict the percent to be 26.9%? So looking at that model again, in what year does the model predict the percent to be 26.9%? Well, the thing that they've given you is a y. It's a percent. So what we need to do is go to y equals and make y equal 26.9 and then see where those intersect. So from here we're going to second trace, which is the calculate menu. We're going to intersect y1, enter, y2, enter, and go ahead and guess, and there we have a 26.9% in 28.9 years. So 28 takes us to the end of the year 2028, and so we're 0.9 into the next year. This is going to be the year 2029. Example 5, women in the labor force. The table below contains the total percent of the labor force that is female for selected years from 1900 and projected to 2050. Find a logarithmic function that models these data and align the input to be the number of years after 1900. So for certain, we have our inputs are going to be positive numbers. They've taken care of that part for us. Let's go ahead and go into the stat and edit what we have in there. And in the Y's, put the percent of women in the workforce. And just double check, making sure that you have no entry errors. And looks good. We're going to first find a logarithmic function that models the data. So stat, calculate a natural log regression. And list 1, list 2. Let's go ahead and store the regression equation in y1. So that model is y equals negative 54.77 plus 21.73 natural log of x. Let's graph the equation and the aligned data points. First off, let's take off that y2 that's from our previous problem, and then we'll do a zoom stat. And they want us to comment on how well the model fits the data. And I'd say, you know, it maybe fits well for the first 3 points or so, and after that kind of just goes off the rail. It undershoots here and then it overshoots here. So it looks like our model is increasing after about right here. It's increasing way too much. We can see from the data that the data looks like it's kind of leveling out a little bit. So it's really not the best fit. Assuming the model is valid in 2024, use it to estimate the percent of women in the labor force in 2024. 2024 is going to be between these data points, so definitely we are interpolating. We don't need to change our window at all. For the year 2024, that's going to be an x value of 124. So we can trace and make sure you arrow up or down so that you're onto the model and not on the plots. And we'll put 124, enter, and there we are. And so that would be about 50%. About 50% of women in the workforce, in the labor force in 2024. So I like this example because one thing that it shows us is that maybe there's a better model that we need to be looking for. Definitely this logarithmic model is not going to be what we want. It doesn't really fit very well. So it gives us an opportunity to explore some other functions that may model the data a little bit better, and that'll be coming up in the next couple of lessons. So go ahead and start your homework and let me know if you have any questions.